let everything begin. So we're going to show the continuous ignition system here as our next demonstration. Then we'll show the same demonstration that we demonstrated to our own investors in our April annual shareholder meeting, upgraded to a newer chemical delivery system that will give a much better experience for everybody, much better power system. And then we'll come back here, show an electric panel on this system in a second attempt, and then we'll have Dr. Manchakari take Q&A, give you a brief presentation on some of the validation work that he's done, and then take Q&A, and then Joe Rennick from Applied Research Associates, defense contractor and science-focused organization that has licensed our technology. We'll give you a brief presentation on his organization, their license, the activities they've done to validate our technology, and then talk about how they're looking to commercialize and help us commercialize BlackLight. Are we good, Johnny? Okay. Go ahead, Randy.
So this is basically the same concept as we had before. We're using a commercially available source of 25 to 30,000 amps, very low voltage. It's like much lower voltage than your battery. Well, not a lot, it's substantially lower. And current runs through these electrodes. You can see it going to one input lead of electrical power going to this rod. The rod is connected by bearings to that wheel. The electric will flow through the wheel to the opposing wheel, back to the opposing rod, and then back into the machine. So currently we're using this very strong, very durable, very commercially available source of electrical power. Then ultimately we would use the photovoltaic converted power to run the system. So as Johnny was saying, we're around 130 joules thereabout because we have to melt the aluminum, encapsulation of the fuel. We're using encapsulation because it's very convenient to put in the calorimeter because it's powder. You have to combine it the way the calorimeter works. We have it mounted horizontally, so it's just convenient to have a known weight and very well characterized material. We've also squished it and compressed it into pellets, and we've ran this material in the calorimeter, and we've gotten up to 800 joules from the similar amount of material in the bomb calorimeter as well. So it isn't unique to the capsule that we get the high energy. In fact, here we're going to be running non-encapsulated material, flowing it through this auger. So it's in a hopper, and Jim will show you here, it's a very small amount. Most of it bounces off the electrodes. Some of it goes down. It gets entrained between the two roller electrodes. The current flows through, and you get the ignition and the bright flash of light. And we can take that and immerse it in water and take it and just strainer it and put it back again. And we ran it over and over and over again, and it works beautifully. So we do have a different system that's fully automated that will recirculate the fuel, and we tested that as a separate component, and it does work very, very well. So we hope to have you back again and show you that automated system. So, so this will be replaced by a PV that would have high voltage that we can transform, or have some circuit element that would take the power and allow the power to go from the PV to the power conditioner and step it down in voltage and step it up in current for that very, very short 50 millionths of a second burst of high current. So there's known circuit elements and switches that work at much higher frequencies than that to do the switching for the ignition at the particular frequency we're proposing to do it, which is 2,000 hertz. So that's about every half a millisecond. So we're going to be turning this on with new source of light, because the light itself lasts about half a millisecond. So then you get complete fusion of light, and you're taking all that light, putting it in fiber optic cables, down converting the intensity to what photovoltaic cells can accept now, and then in the future those photovoltaic cells will increase in intensity. Right now we're looking at about $100 a kilowatt. If they go, there's cells that are running in a company over in Israel, for example, that are 10 times higher intensity capable than the 1,000 suns. They have 10,000 suns. That would decrease the cost by a factor of 10 if all other systems and cost to manufacture those cells were the same. Even if they're incrementally more, or even they're double, they're still cutting the price by a factor of 5. So now you're getting to the point where you almost have a disposable power source because it's so phenomenally cheap. So Jim's going to show you this, and then we'll go over the LED system. Let me get my, just because I'm close. Hold on 1 second, put my earplugs in there. It's not too loud because we're just putting a very, very small amount of fuel. So this only takes about, even with the larger amount of fuel where you get 500 to 1,000 joules, it only takes about 5 joules to detonate this because we're not melting the capsules. So this takes very, very little energy to detonate. Okay? We're going to come back and put a LED converter on that and make electrical power. He's got a 27 watt LED we'll put on that. So if you want to go over to the other lab, we'll show you that. A little bit higher flow rate. And that was a very, very small amount of material. What we have here is, this is just again, something that feeds the fuel in, non-pellet, just puts powder in. You get very, very little of it actually goes into the system. This has a vibratory conveyor, more or less. It looks like conveyed material. And it goes in this funnel, and this funnel has some vibratory actuator on it. Flows onto the wheel, and then some of it gets in there, detonates, and then it's converted. That bright light is converted to electricity using this photovoltaic panel. That's about 70 watts of light-emitting diode light. So all this is slow rates, very, very small amounts of fuel, but it shows the mechanism of how this would work. And for example, what Jim was showing, that would be running at about 2,000 to 5,000 times faster. We've done ignition systems where we've done fuel application and, in other words, ignition and the regeneration mechanical systems, and they work extraordinarily well at 2,000 RPM. So it'd be at least 2,000 times that rate. So then you'll get a lot of light coming out. So. Putting fuel in now. It's just a water-based solid fuel. Again, it's a metal powder, an inorganic compound that forms a hydrate, and it's going into the vibratory feed and then through the vibratory tube and being fed into those rollers. They're being electrified to ignite the fuel. He's just setting the flow rate now.
Ready?
Yeah, you want to shut the lights off? You ready?
Stop.
Can I turn the light on?
Yeah.
Turn the J on?
This fella.
It's going to push it out of the way with the blast?
It's the feed too.
Can you outline it?
So we're ready?
Yeah, you should be good. All right.
Okay, very good. All right, we'll go back to the other one.
Ready?
Okay, it's 27 watts of lighting.
What's the difference between these two? The one we just saw?
He's putting more fuel in. That's 70 watts there. This is 27 watts. And there's a capacitor in there, so it's charging a capacitor. It's kind of leveling it out. So it's got a little bit of load leveling, power conditioning in it. So this is, just gravity fed. It's it's really, the auger is not the ideal way to go, and neither is that type of vibratory feed. But something to show conceptually, you can feed powder in, the powder ignite, it'll make bright light and convert to electricity. So it shows conceptually the different systems of the generator. But there's a very elegant way that you can do the ignition and do it extraordinarily high rate with technological combination, electronics and mechanics that will supplant this, and then that'll be the next step. We'll have very high power production, all automated with regeneration. Then we just need to connect to the PV output for our ignition, and that's it. Just keep improving it. Next thing you know, you'll be driving around with one. Okay, we'll go back and take Q&A. We've had different scientists in to do validation. Caltech, Dr. Rahman Kachari is going to be speaking shortly, and Dr. Glumac at the University of Illinois. And we have, as I said, three very, very well-respected, prestigious engineering firms that are working on making a full commercial 250 kW to 10 megawatts. They have the system engineering designs. That means they have the power supply that'll run off the PV converter, and they have the designs for the electrodes, and we have the designs for doing the fuel feed into the ignition and reclaiming that fuel, regenerating it, and then feeding it back into ignition. And we've tested it at very high speed. That's probably less than 1 RPM that you saw, and This runs at 2,000, at least 2,000 times that. So it's going to be 2,000 times what you saw. Will be very, very powerful. So that'll be making 1,000,000 watts light and about 400,000 watts electric with the appropriate PV converter continuously and doing it regeneratively. So it's a standalone system. And that's about enough to power 2 cars at 267 horsepower car. So that's a lot of power. So the other company we have, so one company is doing ignition system, regeneration system, and taking the power, they're doing electronics and mechanical, those aspects, and the microprocessor controls. So we kind of combined ignition regeneration mechanisms together and the electronic controls thereof. We have another company that's working on the optical distribution system. So it's a system with fiber optic cables and lenses and a parabolic mirror collection system. So we collect the light, channel it into fiber optic cables, and that goes to photovoltaic cells. And it's expandable by increasing the number of photovoltaic cells. So we have the system designed for that, and we can use existing technology, which is extraordinarily well developed and fortuitous in terms of its capability is even beyond what we need. So it's very advantageous that those systems have been developed. So what we plan to do is we're talking to quite a few equipment manufacturers, and we have exchanged licensing agreements with a couple huge multinational equipment manufacturers. Some make everything from F-15 parts to CAT scanners. And they have a desire to include their engineers in our program. But our engineers are moving so fast that we may have something even before they get in sync with us. When we independently, we're controlling that process, and our goal is to make a modular, scalable, commercial pre-production system. We're also talking to very large companies that do component manufacture, like the PV component, as well as mechanical and optical components. And we're working to license them as suppliers, and then looking at assemblers. So you can you'd have contract assembly. There's huge corporations that do that. And then our ultimate business is going to be the sale of electric power through distributors, which we would revenue share with in terms of electrical energy delivered to the customer, in terms of kilowatt hours. So that could be an extremely lucrative business. Even looking at current cost projections, the cell could pay itself off in a month, so you don't have the 20-year financing burden you have with solar on your roof, with change of ownership control and things like that. And so it could be a very, very profitable endeavor. This is some of the structures we're looking at in terms of having the original equipment manufacturers make the equipment for BlackLight. We would own it and then lease it to distributors, and then there'd be a grant in that lease of certain patent rights to deliver power to consumers under power purchase agreements. And then we would share that revenue. This is one representative model. You're looking at a 1 megawatt generator, and what the revenues could be off of that is quite extraordinary. So you're looking at hundreds of thousands of dollars net to BlackLight and to the distributor for that type of power generator. And that would fit very nicely into an industrial application, or a very, very, say, industrial complex and commercial complex, mini grid. Go very nicely in terms of selling power under power purchase agreement to maritime applications, freight moving, many passenger mode of power, many applications, even for that larger scale unit. So we're looking at primarily the sale of power as our main source of revenue. So that said, I'll take any questions, and then we'll have our other esteemed guest here. do some talking. Yes.
You mentioned that the dominant cost, the production cost for the sun cell is the concentrated photovoltaic cells.
Yes.
If you wanted to get to market quicker with a cost-effective device, and since there's all this infrastructure existing out there with coal power plants and so on, why not just thermalize the energy and have a plug-in replacement into their boilers and get it out faster into the existing infrastructure? At least as a first product.
Yeah,
How do you get the sun cell all figured out?
well, I think the issue there is if you're going to build into the central generation system, you're looking at economies of scale. Those turbines are typically 100 million watt or several hundred million watt. That would be very, very expensive, and it would take quite a number of years in terms of trials to get the statistics on the payback, the duty cycle, how long it sustained power production without maintenance or without repairs being required. That's a model we could look at, but I think we're going to have systems. One of the OEMs we're talking to said with their engineers, if we do a license with them, they thought they could have multi-megawatt devices in field trials in less than a year. Those big power plants are huge. They take up acres, and those turbines are very, very expensive, and then you have to make a boiler system. And
I'm just saying, since they're existing and out there already, there's a lot of people that are going to want to try to reuse them somehow. So
I know what you're saying, and it is a possibility, and we do have licenses with companies, utilities, and huge multinational chemical company and independent power producer, and that might be a viable option. We're agnostic. We could do that. Again, you're wed to the central grid model. So if this is generating power, even at the same price for generation, you're still spending 6 cents for transmission. So it's a question of competitiveness and just the huge scales that those central generation plants require to get an economy. That my take on it, based on where we're at, is this will be out in the field long before you'd ever even have that built.
So you'll just get there faster with the sun cell, given all the legacy processes you'll have to get through to get it.
Just the huge, the scale of that is pretty daunting. And then you'd have to make a boiler, you have to make steam, you have to make steam under controlled conditions, then you have to mate it with existing turbine. Those things are very, very big. They're like as big as this room. They're very expensive, and they've been set up to run coal-fired boilers. So you'd have to take whatever aspects this are. Its power density is 10 million times higher. So it's good from the perspective you get high heat transfer, but obviously you can't use a coal boiler and just put this in it if it's 10 million times higher power density.
I guess it's something you can at least fall back on if there's an engineering challenge with the concentrated photovoltaic cells that you weren't.
Oh, I agree. You can definitely do that. But then you got to ask yourself about the photovoltaic industry, because there is a thermal photovoltaic industry. There's a plant out in, I don't know, somewhere in Mojave Desert that NRG did. That they have. I was talking to Crane about it. He's the CEO of NRG, and he was saying that they have a power plant like 25 stories in the air or something. They have these mirrors. He said it's the most incredible thing you could actually fathom. It's
molten salt or something.
Molten salt, and he said it's the most incredibly complicated, extraordinarily expensive thing, but it's paid for by the government. They just get paid so much a kilowatt hour, so they don't really care. But so it's guaranteed money. But it's he said it's just incredible that anybody would build something like that. And you ask yourself, the parabolic mirrors used to have Stirling engines. And there was a huge DoD push to put Stirling engines on parabolic dishes for pumping water and things like that in third world countries. But they've been supplanted by PV. So if they're so great, then the concentrator photovoltaic industry, it wouldn't be a concentrator photovoltaic, it'd be a concentrator with Stirling engine. or some heat engine. But to get economies of scale, you typically have to go very, very big on those thermal applications. That's why they have, that's a multi-100 million watt plant, that one in Mahoney. It's the only way you can even get even in the realm of something reasonable cost-wise. Yes?
The idea of having your electric vehicle plug into your house and power your house, pay for itself. Have you talked to Elon Musk about this?
That would be one of our...
The fact that you can, the concept that you can power your house with your electric car to pay for your electricity, to pay for the car. I wondered if he had spoken to Elon Musk.
Yeah, we're in contact with people that are involved with Tesla Motors, and they're building a multi-billion watt or multi-billion dollar lithium ion to get the wattage and the reliability. You know, enough production for those cars. You know, they're up around 200 kW, which is a lot of batteries. And you know, you got like 24 watts per cell. So they're going to put in some production. They're looking to put it in different states here in the U.S. and mainland. You know, it gets back to our strategy. We want to make sure we had all the systems engineering design and have things up, be in at least a detailed engineering design stage, because it's kind of hard to approach a widget operation and say, well, we got something on the drawing boards. We want to go to them and say, you know, we got a better widget than a lithium-ion battery. And I think that maybe the next generation, which we hope to have, we're going to start working on that tomorrow, and we hope to blast through that pretty quickly. And then once we have something that's running continuously, all automated, then I think it's probably a good time to say, you might not want to build that multi-billion dollar battery company. Just wait like half a year until we get a little bit further advanced, and you could use our electrical source. But they don't really make the system anymore, an assembler. There's another company we're exchanging agreements with that actually make all the electric systems in that vehicle, the motors and the controllers and the like. They kind of just assemble it, and they buy the lithium atom. I think they're getting from Panasonic now, but they want to make their own plant.
With the engineering challenges going our way, the prototype that we see up here, I know we were thinking back in March or April, it'd be 6 to 9 months that we have that working prototype. Has that time span shortened because of things?
Well, the engineers are saying we actually had everything break our way. Like the engineering's going really, really well. So we'll have more information on that in a few more weeks because they're done the design engineering. Then we're going to get into the detailed engineering. I would say the mechanical part, we should be on schedule for that for sure, but it's just a question of how long it takes for the PV side to be put together. Get our light source, hook the PV, have the right output of the PV for the ignition system primarily. And so we're working with them now, but you know, it's just a question when they can deliver their part and then get the optical system built. So we really don't have any information on the timing of that. I know if you go to the entirely new array, they're saying they like 6 months. They build entirely new cells and new dense array. But we can use what they already have. They're saying, you know, 3 weeks, something like that, delivery time. So it's reasonable. So we have to see how the PV and the optical distribution system timing works out. The other mechanical system, I think we're definitely on schedule for that. Yes?
With the validation that you have achieved, is the company planning to or pursuing the patentability of the fundamental patents which were denied?
I don't think the denied patents are any relevance to this because we're filing all new patents. They're entirely different. I just filed one yesterday. So I think we're in really, really good shape with the patents. You know, some of the arguments the patent office made is that, and they're now since abandoned, so I can talk about them. I mean, it's basically they're saying it's purely theoretical. There wasn't really system design, and at least that was their argument. I would argue counter to that, but you know, they had their view on things, and we've since moved on to something that's, just to even give you an idea relative to electrochemical, it's 1 billion times higher power and 1 trillion times higher power density. So obviously we're going in the right direction in terms of power. So even if the patent office issued them, we have something that's so phenomenally better that they're actually costing themselves money. We'd have to pay them maintenance fees. So I think they actually did themselves a disservice. So I think we're in really good shape. I mean, I like the patent position we're in. Our firms looked at all the cases. We have a board member that I sent them all our filings to, and he's involved with it. He's a very, very capable expert in patent law and what you have to file in terms of preparing for in preparation for future litigation if that ever occurs. So I think we're in pretty good shape with patents. Yeah.
You're capturing the light energy. What about the heat energy? How big a radiator would be on the vehicle to dissipate all the heat that's being generated?
Well, you know, even your car is at least a couple 100,000 watts, and your radiator does pretty well. In cars like maybe 25% efficiency. The rest is heat. It's either going out the tailpipe or through the radiator. And our engineers have looked at it. It's not really a problem. It's not that big a problem. And if you look at we have heat rejection on the electrodes. We're going to have stationary hubs and a water circulated heat exchanger. The way we look at it now, totally adequately handles the heat load for that amount of power going through it. And the foldable take component, which if you say you have an incident 1 million watts and you have 400,000 converted into electricity, that means you have 600,000 heat. Well, that's exactly the same problem they have with those concentrated photovoltaic. Whether it's sun or our source, it's the same. And if you look, the concentrator photovoltaic has a heat exchanger, and then they have water circulation with a radiator on the back of the parabolic dish, and it works fine. So they have to keep those pretty cool because the photovoltaics operate in a lower temperature range, and they're all rated, field tested at tens of millions of watt installations running all the time, and they work fine. So it'll already come pre-packaged with the heat rejection system, the PV part. Yes.
In terms of a building unit, the thermal energy is a useful byproduct.
Right, it is.
For heating or air conditioning the building.
Sure. Yeah.
So you don't want to radiate it, you want to have an output that is thermal as well as electric.
And they have coolant lines on the PV, and they have coolant lines on the electrodes, and then we can take that heat and put it in a heat exchanger and use it for some commercial application.
The last time I was here, you were speaking primarily about plasma conversion.
Yes, I addressed that earlier.
Now you're really speaking more about light.
Light, and that was because we measured the pressure, and the pressure is only on the order of about 10% that of atmospheric pressure. It's very, very small pressure, and if you look at the pressure volume work, it's only about 1% of the energy, which is good because if it's pressure volume, you know, that blast we saw, most of it came out as a flash of light. If that were really pressure volume work, it would cause a lot of destruction, and so and it can be readily converted into electricity using existing technology. Like if we use plasma, even though magnetohydrodynamic has been shown with coal-fired plants with seeding. In other words, the fire in a coal-fired plant is not hot enough to ionize the gas, so they put compound, like a salt compound, so they have ions to make it conductive, and then they expand that high pressure through magnets and they convert it into electricity. That technology already exists, but it's using pressure, volume, mechanics to make heat. The same way pressure would turn a turbine, that pressure would be pushing those ions through the magnetic field to make electricity. We have very, very little pressure component to our power, which is good.
Have you abandoned that concept? Or?
Yes, we have. We've switched to photovoltaic conversion, which is vastly, vastly better in terms of cost. We don't have to use superconducting magnets. We don't have to use electrodes. We don't have electrode destruction by being in contact with plasma. And we get incredibly high conversion efficiencies with existing technology. And if you look at it, magnetohydrodynamic would be a pretty big power converter with the magnets and the like. You can get, with the 2,000 sun cells they have now, you can get 1,000,000 watts off a square meter, the thinness of a cardboard. So you were even talking about thermal plants. Thermal plants have very, very low power density. Just imagine how incredibly compact that is. I mean, even if take an internal combustion engine, you can get the equivalent of about 3 car engines with this little thing that's that thin. I mean, that's really amazing. And it's all electric. So,
So what transpired from the last meeting?
we measured the pressure. The pressure is very low. We measured the light component of the power, and it's essentially all light. Fire isn't that way. Fire would love to be all light because then they could use PV. But they got to boil water, put it through pipes, turn turbines, condense it, have big cooling towers. Many acres for a plant like that. And maybe $100 million, $1 billion to get the economies of scale, to get the cost of that equipment down, or the logistics to have equipment that will last 20 years so you can pay it off. So a lot of the cost in a power plant is circumvented by going to this PV, and it's very compact, and the other thing is it's autonomous. Like, who's going to run around with a steam turbine in the back of their Tesla? You know, it's so elegant. You get rid of the lithium-ion battery, you have a PV stack, it's all very small, it's all electric. It's an incredible breakthrough. I mean, in other words, the engineering is breaking our way on every aspect. So it broke our way. I mean, we were like, you know, now we got to make a magnetohydrodynamic converter or go to steam. And we're like, oh my God, we can use foldable tape. That's such a godsend. I can't even tell you. That is such a gift from nature. You can kiss, you know, the earth for the rest of your life and not have enough homage to that breakthrough. Yes.
The explosion chamber is going to be in a vacuum, as I understand it. So it'll be
Yeah.
a quiet box.
Oh no, we can put sound dampening, or we can put a vacuum around. It's not a problem.
But I'm suggesting maybe when they're pulling, you know, making the vacuum, they're actually siphoning off the oxygen that's coming from the water.
Oh, we'll just put a little hydrogen in there and burn it in the plasma. Not a problem. Okay, so we'll have some other guys up here, and then, you know, I can come back for some more questions. So Dr. Chari, this is Dr. Raman Kachari, he goes by Chari, just for you know, ease of communication. I've got that down. Seats. Oh, yeah. Sorry. So Dr. Raman Kachari, he actually has experience in our area. The inorganic chemistry is a very esteemed professor at Rowan University, and he's done a tremendous amount of research. He's got all kinds of incredible projects going on. Over $10 million in grants. I mean, he's got really international collaborations going here in Asia and India and all over the place. So he's we're really honored to have him here. Really appreciate you coming to speak today.
Thank you very much. I've been working with Randy for almost 10 years. When I first learned about this entire new chemistry and physics going on, I was puzzled. And I was thinking that how can quantum mechanics be so wrong? Because I teach my kids about this. So over a period of time, of course, I was very skeptical in the first year. But the kind of person I am, I don't shoot down. I want to do it myself and see if that makes any sense. So that's where my journey began with BlackLight power. And we have gotten into some experimental work done in my laboratory. And as a chemist, we look for some indicators on whether the state of hydrogen is new or has it been known before. Hydrogen is known to humans for many years. It's one of the first elements known to humans. So we know a little bit more about hydrogen than other elements. So we do have facilities at my university, such as nuclear magnetic resonance spectroscopy and all the thermal measurements, what Randy has talked about. We do have those facilities. So we kind of repeated and replicated those measurements in the laboratory. And we were pleasantly surprised to see this new form of hydrogen in the form of the nuclear magnetic resonance spectroscopy peaks, as well as the heat effects, the measurements. So we're fairly convinced that there is a lot going on here. And then Randy talked about this, the new form of light that is coming out of the metal oxide water interface. By training, I've been working in the metals and metal oxides for almost 32 years. So I do know a little bit about the chemistry that happens between the metals and the oxides. We have published about 200 papers in the past on these oxide materials. So what I was looking very carefully was to see if there was any transformation when you bring the metal oxide and water. What else can happen? So what we have done is I've watched very carefully the starting materials and the final materials to make sure that there is no other chemistry other than the transition of this hydrogen atom, inter-electronic transitions. So that was very convincing. Again, we looked at the power X-ray diffractions before and after. We looked at the heat effects. We looked at the Raman spectroscopy. And all these measurements, what we find is the metal and the oxide has not changed its form. It is just the water, or the hydrogen of the water, that catalytically got transformed into a new form of the hydrogen that we talked about. So that was pretty convincing. You can take it from me. I'm an oxide chemist for 32 years, and I can pretty much vouch that this is really a phenomenal observation what Randy has made. So my expertise primarily is limited to the chemistry and to the physics. So if you have any questions for me on these things, I will be glad to answer. Yes, sir.
So there's no transmutation, but when we see a spark, what appears to be a spark, the metal is it actually burning? Are we seeing sparks like you would from a sparkler?
I think the purpose of metal, maybe Randy can talk the physics of this, is to just allow the current to pass through. If you don't have the metal, in fact, they have done lots of experiments. I've seen some experiments done with just metal and metal oxide without water, right? Maybe we should have done a demo here.
Yeah, we have some other control materials.
Some experiments. So if you don't have the water, right? You just have the metal and the metal oxide. You don't have the spark. Nothing happens. So that was,
well, we run the calorimetry is run in argon. There's no oxygen. And then we have this enclosure, we can put an argon, we have an enclosure, we put argon around, so there's no oxygen. You see the same phenomenon. So there's a reaction with some of them with water, but silver won't react with water, and there's copper won't react with water, extraordinarily stable compared to water. It actually takes an enormous amount of energy to make the oxide in those cases, and we still get the 800 joules of energy, and we still get the bright light. And then we do, like I said in the beginning, we do different types of analytical tests, like X-ray diffraction and X-ray photoelectron spectroscopy. And the water reaction with these metals is a much longer time scale because they get an oxide coat, and you have to penetrate that oxide coat and go deeper with the oxide. And at 0.5 millisecond time scale, it just doesn't react. We could it's just too short a time. It's like burning a piece of wood. You tried to burn wood for 5 times 10 to the minus 4 seconds, it wouldn't burn either. I mean, there's just not enough time for anything to really happen. It won't get hot enough, and it won't ignite. Like, even when you try to burn a newspaper, you got to kind of hold the match there a little while. I mean, that's like seconds. Talking very, very small fractions of a second.
The metal is not burning?
There could be some burning. I mean, but the reaction that you're seeing with a bright flash of light, it's extreme ultraviolet light. Burning cannot make soft X-ray, extreme ultraviolet light. And then we run an argon, we see the same thing. But you can take a welder, if you look at a plant like a GM and you see some sparks, but they're kind of these yellow sparks. This is like the whole thing lights up with white light, and we get an extraordinary amount of energy. And we showed you control. I mean, that's what the welder does. Nothing happened. We put the, and we have other fuels that are water-based, very, very similar chemical composition. We run it through there. Nothing happens. The same thing as what you saw with the silver. So it's a no question. There's an incredible phenomena going on, And any kind of thing burning with oxygen in a commercial system, we'd have it in the argon atmosphere or vacuum. But we would not have oxygen in a commercial system.
And on top of it, we also have done the X-ray diffraction of the samples before and after.
Right.
And from the diffraction, we can't tell that the metal has really worked. If it don't, then we would not see peaks of the metal. Yes.
Have you tried to convince any of your academic colleagues of the validity of the underlying physics?
Excellent question. In fact, that's how we started with PLP and landing jobs. Our idea is we should put everything on the web. So for 5 years, we have put all the information, how we did the experiment, what we see, and what our thoughts are on the observations. So far, I have not received any negative comments from any of my friends. And apparently other people also have done these experiments and they have validated the observations. So when I talk to my friends, I think they at least, to my own community, they give me an ear to me because they want to see what I think about the process. And it's quite likely it's possible. But I think it's going to take a little time to build the consensus among the community, and we are trying to look at this very carefully. Thank you for asking the question.
Okay, very good. We have, thank you very much. That was excellent. That's good insight. Another soldier in the field there trying to win the energy war and save mankind from cold death. We appreciate that. It's just a minor hobby. We have Dr. Rennick here now from Applied Research Associates. He's going to talk about, they did some validation as well, and his insights into technology and potential applications that they see. Okay, thanks.
I thought you might be interested in the thought process that a company like Applied Research Associates goes through as a defense contractor in looking at some technology like this that challenges, basically standard accepted models of quantum mechanics. This is pretty agonizing, actually, because all of science is so embedded in the old ways of thinking, standard quantum theory. And before I mention the details of that ARA, my own background as an engineer, but I did take quantum mechanics courses. And the first time I took a detail, kind of a graduate level course, it's in the area called physical chemistry, is what the chemists call it. And I had taken a sabbatical from the Air Force Weapons Laboratory back in 1986, 87. I think Randy was just getting out of Harvard at that time. And what I had envisioned is taking a year off from the lab after 15 years of this brutal work. This is the Cold War years. We don't want to go back to the Cold War. We really don't. And very intense research programs. So I thought I'd take a year off, go down to New Mexico Tech, and go skiing every weekend in the winter, and go hiking in the mountains every weekend in the summer. It didn't turn out that way at all. One reason is because I took this physical chemistry course. Then I was doing some research under a former director of National Nobel Labs, which is a fantastic opportunity. Well, I took the course, and I would go in and talk to the professor, and I would ask him questions he couldn't answer. I said, why do we make these assumptions? He didn't know. Isn't there a better way to think about this? Well, this is the way we've always done it. He's a great guy, don't get me wrong. By the time I got done, I says, no, this is not the way the world works. And anybody is crazy to think that this is the way the world works. Then a physicist friend of mine, a few years later, asked me, have you heard about this guy named Bills? He's talking about some kind of fractional quantum state chemistry, hydrogen, at lower energy levels. I said, no, and he gave me a website. And I took a look at BlackLight Power, and I said, he gets it. He's challenging fundamental theory, and I went through a period of about 3 years of doing my own due diligence. And I was convinced at that time that he's got something here. This is really good stuff. I was with Northrop Grumman at the time, and I began talking to government offices, DOD offices, and finally met Randy in the spring of 1999 when I visited these laboratories that he had opened up, I guess, the first of January, early in the year 1999. And when I left, I was convinced that, you know, number one, government scientists need to come in and take a serious look at this. You know, my plan at that time was get a few chemists I know, physicists I know in the military labs come in, and they'll say, yeah, this is great stuff. Introduce them to Randy, and then I would walk off into the sunset and go skiing and hiking and that sort of thing. It didn't work out that way at all. I think you've already gotten some sense of the resistance that the scientific community has to Randy's work. I wish, if you had 2 hours, and Randy's not going to let me do this, I could talk about the elements of this theory and how beautiful it is, how it suddenly connects back to Maxwell and Newton. And science went off the rails in the early part of the 1900s under the influence of the philosophy called rational positivism. And that had an influence on the thinking of the scientists at that time and ever since. And that's why we have silly things like string theory. Now, if you say, hey, I heard a guy talking at BlackLight, and he was saying that strings theory is silly. It is because it's not physical. You heard Randy talk about his theory is physical. That's the key. Is your theory physical? Some people won't even know what you're talking about, but that's the key. So, BlackLight and ARA have been talking for some time, about 7 or 8 years now. ARA is a science and technology engineering firm. Most of our business is with defense. We've been in business about 35 years, around 1,100 employees, a little over 200 billion annual receipts or revenues. We have an interesting culture. It's employee-owned. Senior management is very risk-averse. We are also mission-oriented. And the reason is a lot of our people, including myself, are ex-military. And in the military labs, which I've worked with for 40 years now, you go down to Eglin, the Armament Lab, you go to China Lake, you go to Indian Head for Navy. The people that go to work there are thinking about the warfighter and warfighter problems. What can I do for the warfighter, basically for the country? And so when I go down to Eglin, talk to the lab people down there, you're always hearing the fighters overhead, the noise, and the afterburners kicking in. And you get a sniff of the old jet fuel fumes blowing off the flight line. And it gives you a sense of the reality and the intensity of their level of thinking. But what's interesting then is when I talk to the lab guys about BlackLight Power and the fact that it's controversial, they say probably what an investor would say, I don't care about the controversy. I don't care about the physics. Does it produce energy? Is it cheap and is it clean? And we got a lot of it. We have a lot of water around. So the answer is yes, it's cheap and it's clean. And Randy just showed me I get a lot of energy out of it. I said, that's what I care about. I got problems and I've got to have solutions. And we are busting our cans every year with minimum budgets, especially the last 3 or 4 years, it's just another nightmare for research for the DOD. We have big problems with many big solutions. Well, BlackLight Power brings answers to those questions. So when I talk to the engineers and scientists in the labs, and the DOD labs, then they say, we don't care about the controversy, just show us what you got, show us your stuff. And now the other criteria though is they say, we're not willing to put R&D money into this work until a contractor like ARA makes enough effort on their own, due diligence and validation. Do that, show us what you got, then we can talk. So it was that kind of thinking that led to the license agreement that we signed a little over a year ago that gives ARA rights to use the solid fuel technology, much of what you've been seeing here, for government purposes only. And so we are now going through this process of validation. We have completed 2 validation studies with 2 major universities, with the major well-known research facilities and labs at those universities. And we have confirmed that this amazing thermal energy generation from materials, simple materials, common materials, that you simply cannot explain where that energy came from. And so we have basically validated that twice. In fact, with one of the universities, I think Nick did about 6 or 7 experiments, $3,500. So you may ask, well, why don't other universities, why don't other research organizations, it only cost me a few $1,000s just to do a simple experiment to demonstrate this excess energy of this unexplainable heat source. Why don't they do that? Well, that's because you're getting back to the nature of the way science is done. It's like a religion. We have a high priesthood. And the priesthood says what's true, what you can do, what can be funded, and that's the way it works. It is a shame. And I'm looking forward to tearing down that. In fact, I guess that's one of the things that keeps me going, is not just getting this technology in the hands of the Lord, but tearing down this priesthood and showing everybody what the truth is about the way nature works. Monday morning, I looked at the Albuquerque Journal, and every Monday they had this Business Outlook publication. And there's a consortium of companies who are interested in technology that formed kind of what you would call a list called the Flying 40. And they have criteria by which they evaluate all the high-tech firms in New Mexico and rank them according to this list and that criteria. And for probably the last, that Flying 40 activity has been in existence about 17 years now. For the last 10 years, ARA has been, most of the time, #1 or #2. So it's a big deal. The governor comes down, have a big meeting, banquet with speakers. And so ARA has worked hard to earn the reputation that we have. And I've had a number of different laboratories say we are willing to investigate the BlackLight power technology because we trust ARA. And that's very rewarding. It's very gratifying to hear that kind of response. So we worked hard to earn their reputation. Okay, let's see. Just a couple of comments. In having been working with BlackLight for 15 years, seeing the experiments, have a pretty good understanding of what's going on here. And in particular, the power production technology that Randy has just showed you. From a consideration of the mechanics, the physics, processes that are involved, there simply are no showstoppers. This is taking existing technology, especially in the photovoltaic technology. Billions of dollars have been invested in this, and here it is, right off the shelf. Plug it out, pull it off, plug it in, and use it. So a lot of that technology that's going to make this system work has been developed already. So I think, as far as I can tell, there just simply are no showstoppers here. Let's see, I think that's most of what I wanted to say. Let me check. Yeah, okay. I think one of the questions earlier kind of spoke to this. The transition from where we are today is sometime in the future when all of the old infrastructures like energy, fuel distribution, power distribution, when they have been taken down and replaced with BlackLight technology. It's easy to envision what that might look like because it's going to be probably primarily distributed. It's in your car, it's in your garage. And it's, you think about the natural disasters that have hit our country, especially the Northeast in the last few years, power outage. Everybody's got their own power. You don't have that problem. And you start thinking through the consequences of what this will do for us. It is going to be changing the world in many ways. One of the challenges that we'll have, and I say this first because I think it's interesting, but number two, because I think it's important, is the way that transition takes place. You can't just go out there and say, okay, on January the 1st, 2018, we're going to shut down the grid, and then we're going to start up with a distributed system. No, it's going to take generations to make that transition. The capital investments are so huge that we've got to find an economically viable way to work our way through this. So I just find this, I guess the point is that I'm not going to solve that problem. If somebody in leadership has got to start thinking about how we do that, and God help us, we can't let the government do this for us. They'll screw it up every time. Yes, sir.
What are the parts, of the validation process?
I'm sorry?
What are the areas of rejection validation process?
Solid fuel, energy production. Glad you asked that because I want to make it clear. We have specific areas of technology, ARA does, that we want to pursue with the government and with specific customers. I can't tell you who they are or what that technology is. It's not exactly what Randy's talking about. Okay. Then a couple of other comments, and then I'll, go ahead. Any questions?
So what concerns me, I'm assuming you're talking weaponry because you're talking about warriors. So the trepidation that I might have is that we're looking at energy here. I would assume you're looking at energy for a different purpose. Is that, do those things beat each other, or do they work against each other?
I would say they're complementary.
Well,
I think that the work, well, I think the work that we do, which is kind of a little different situation, and a different product, will be useful information for the energy production. Where we find that what Randy has done so far is very interesting for our application. There's going to be a flow of information, and I think there are challenges in the different area. But let me mention right quick, I did a study, actually it was for the Air Force Research Lab a few years ago, on what would it look like to take a Boeing 787 Dreamliner. Has anybody flown one of those things? I guess they're pretty nice. The 787 Dreamliner. And basically replaced it. What I was looking at initially was the fuel cell technology, the site technology, and the kind of power energy density, power densities Randy was producing, or what he expected it to be. And basically, one of the interesting numbers that came out of the study is that the maximum power on takeoff for a fully loaded 787 is around 87 megajoules, or megawatts. Okay. Now you take that in terms of the energy levels that Randy is talking about and how big they are, you can see this completely changes everything for flight, for powered flight. And in particular, the fact is you don't have any jet fuel on board. And this is about 1/3 of the total weight of the aircraft and passengers and airframe on board. And no more big fireballs. And I like that idea myself. Because I used to fly in the military through fighters, and I saw too many fireballs and lost everybody's friends. The idea of having to be able to fly like that and not have this huge tank of gasoline behind you, that's kind of nice. So I think aviation safety will be transformed with this technology as well. Okay, that's just an aside, but there's so many areas I've looked at like this that say, well, what does, put the numbers down. Give me some hard numbers. What does it look like when you go and do the engineering and the scientific studies? And here's just an example. And of course, the benefits are pretty fun. Okay? Yes, sir.
Has the Department of Defense financed any development application?
We sure hope they will.
Not yet.
Not yet. We have been talking with them for years. And they say, do your due diligence, do your validation work, and we're ready to talk. And we are in that process now. In fact, we should have be having a meeting with 2 or 3 DOE offices within the next month or two. Right here. Yeah, the process is engaged. Yes, sir.
What is the risk that somebody can figure out how to create a weapon mass destruction with this and multiple die non-state actors?
I'll just say that we hope they don't. I can't comment on it. And yes, that's a legitimate concern. And I will say it will be looked at. Okay, thank you, Randy.
Okay, thank you. Okay, maybe a couple more questions. I know everybody's probably dying for lunch and whatnot, and kind of, I guess we're sort of on schedule, maybe a little bit over. So any final questions? Yes.
Yes. What kind of interest are you getting from the utilities in this technology? And have you had any contact or conversation?
I've been talking to one. It's kind of a progressive utility, and they said, as they said, we have a couple OEM agreements we're exchanging back and forth. They said once we had that signed, then they'd want to do a deal with us for distribution. That's kind of at their top executive level. They've given me that feedback, and then I got I was on a call yesterday with them. They've asked a bunch of information about the technology, so they're definitely tracking it. And there's certain markets they'd like to introduce it into that are sort of autonomous in terms of the grid, and more progressive markets, more aggressive in terms of allowing deployment of new technologies. But, you got to keep in mind that the grid is just a fraction of % of power generation, so it's an important market, but it's not enormous in the grand scheme of things. And even everything, if you look at worldwide fuels and the like, oil is still 50% of all fuels, and that's including wood, biomass. There's a huge amount, coal. Other countries aren't fortunate to use oil, but even at that, the world's still 50% oil. So it's a lot of the world's powered by oil, and that's a big resource in terms of its value as a commodity and replacement thereof. Yes.
Have the oil companies come to you to buy you out and get you out of the market?
Yeah, I talked to a couple oil companies, big oil company, one a year ago. It's hard to say how they're going to react. This particular oil company is an enormous oil company, and the scientists surprisingly were very, very interested, but the upper echelon management was very, very disinterested, forbid them from pursuing it. I can kind of see why. I mean, some of these oil companies are fully integrated chemical companies, but they, they drill for oil, they refine oil, everything's about oil. So then you're probably better off starting with nothing, because at least then you don't have baggage. But they have enormous amount of money, and if they decide to get behind this, I mean, they like tens of billions of dollars. Some of them even buying their own stock back at that level. They could make this happen overnight, and they would be hugely successful. And they make incredible money over what they're making now. I've done some models that they charge by the mile. They could make vastly more money than they're making on the margins of oil.
What are the other industries other than energy that you can see? You had mentioned semiconductors, physical light, and so forth, that are going to be that you can see be revolutionized by what you discovered here.
Other applications? Other inventions? Well, I don't want to dwell into that now, but there are going to be extraordinary inventions. I mean, when Maxwell predicted electromagnetic waves, and you had radio and TV and power transmission, power generation, electric grid, all kinds of stuff. I mean, you know, there's going to be enormous step function type paradigm shifting innovations. BlackLight should lead that, of course. Since we're so far ahead of everybody else in the world, we might as well stay that way. Yes?
That was kind of leading into my next question about the photovoltaic. That's not the only methodology that you have to go with, right? There's other ways you can distribute that power.
Power, in other words, we're looking not to invent a new power converter, but to use an existing converter. And it just so happens you can have energy release as heat. You can have energy release as a phase change. You can have it released as some stored energy, maybe transformation of some phase transition or something like that. You can have some boil and turn to gas. There's a lot of ways you can release energy, and that energy can be manifest. It just so happens that this energy is almost entirely light in the visible spectrum for photovoltaic conversion, and that's a very good thing. But yeah, if you ever wanted to do steam turbine or magnetohydrodynamic, you could always heat something, expand gas that you seed. I mean, there's all kinds of ways you can do it. You can take energy and convert it to another form. It's just.
Do you think
but
this
most,
is the quickest and most efficient at this point?
I think anybody in the power business, like I said, they would take Maxwell's equation, they'd kiss it the rest of their life, and they couldn't even do it justice for that gift of nature. You can just take $1 trillion technology off the shelf and just readily just slap it on like we just showed. There's no boiler, there's no condenser with steam. It doesn't look like 3 Mile Island, it just looks like a little panel. You can imagine, stick that in your car, take your huge SUV that you drive, just put that in the back, it'd be a little suitcase. You know, in the end, it's going to be probably about the size of your wallet. I know you have a huge wallet, but it's an average wallet. That would take you anywhere you want to go forever. Okay, thank you very much. Appreciate you coming. Next one should be really awesome. Hope you all make it.